Welcome to the future of electric mobility in India. And this infrastructure keeps growing exponentially. Card allows the users access to the station where they can place the drained batteries in the empty charging slots. The battery swapping process is extremely easy and takes less than a couple of minutes, saving users on cost as well as long hours of recharging a conventional fixed battery-powered e-vehicle. Service subscriber and become a part of this revolution.
Audio Jungle.
Assalamualaikum warahmatullahi wabarakatuh.
We are from Group
9 from class D.
My name is Nabila Abdullah Nisranti with student ID 121250122.
I'm Shaisa Latifa with student ID 121250128.
And my name is Hasbaulam Faridun with student ID 121250141.
And today we will present our technological innovation titled Efficient EV Powering with Battery Substation, Swap in Seconds, Drive for Miles.
As the use of electric vehicles continue to grow, the need for a charging system that is fast, efficient, and easily accessible becomes increasingly important. For the reason, we introduced an innovative solution in the form of a battery swap station, which allows users to replace their vehicle's battery within minutes, without waiting for traditional charging.
Through this innovation, we aim to contribute to the development of a more practical, environmentally friendly and sustainable electric vehicle ecosystem. Without further delay, let us begin our presentation.
The growth of fossil fuel-powered vehicles in the distribution and transportation sector has led to increased carbon emission and air pollution. The transition to electric vehicles is a sustainable solution, but its adoption is still limited due to uneven battery charging infrastructure and long charging times. The battery swap station system offers an innovation to reduce charging wait times and improve the operational efficiency of electric vehicles. This study aims to analyze the potential application of battery swap stations, model route and key optimization, and review professional ethics and intellectual property rights or IPR awareness in transportation technology development. The methods used to include literature studies, linear optimization, modeling, key system, simulation, and matrix-based decision analysis. The results of this research are expected to show an increase in the efficiency of electric vehicle use, a reduction in waiting times, and a positive contribution to carbon emission reduction. These findings are expected to form the basis for recommendation for the implementation of an effective and sustainable battery swap station system, while also strengthening ethical awareness and IPR protection in transportation innovation.
Background are transportation plays an important role in human mobility. This is because transportation is an important means of enabling humans to move from one place to another more quickly and easily. With various modes of transportation such as private vehicles, public transportation, and trains, airplanes, human mobility has become more effective and efficient. Transportation not only facilitates daily activities such as going to school, work, or shopping, but also opens up access to broader opportunities such as tourism, social gatherings, and economic development. Without good transportation, distance and time would be major obstacle in meeting human needs and desires. Therefore, transportation acts as a key connector that drives the social and economic life of society. Transportation is also important in responding to emergencies as quickly as possible.
Due to traffic congestion issues occurring in various parts of the world, ambulance response times are negatively affected. Emergency services that are directly related to human life and health cannot be equated or compared to regular service, where every minute and even every second can play a crucial role in determining the survival of patients. Motorcycles as an alternative mode of transportation are very effective in navigating dense and fast-moving environments, thereby reducing the time patients spend waiting for emergency care and offering faster response times, especially in cities with high populations where traditional ambulances experience difficulties.
Transportation also plays a very important role in the distribution process of goods because it is the main medium for distributing goods from producers to consumers. With vehicles, goods from distributors can reach consumers quickly and more efficiently. Through various types of vehicles, whether land, sea, or air, such as trucks, trains, ships, and planes, goods can be delivered quickly and safely to various regions. Even those that are far away, a good transportation system keeps the supply chain running smoothly, ensuring that products are available in the market on time and in a good condition. This will certainly help economic growth because it can facilitate market access, trade, and accelerate the distribution process. Thus, transportation not only facilitates the movement of goods but also supports economic growth and efficiently meets the needs of society. Therefore, vehicles or transportation facilities must be carefully considered to continue supporting access to goods or services and fostering economic growth.
However, the vehicles commonly used are fuel port vehicles, which are one of the large contributors to greenhouse gas emission, especially carbon dioxide. In 2021, transportation contributes 24% of global CO2 emission, making it the large contributor to climate change. Road transportation also contributes 16% of global direct CO2 emission in 2022, the majority of which came from passenger and freight activities. Urban bus systems that are highly dependent on fossil fuels are a major contributor to greenhouse gas emission. The global over-reliance on fossil fuels for transportation has reached alarming levels, causing serious environmental and health impacts. Fossil fuel port vehicles have driven most of the emission from the transportation sectors, contributing significantly to air pollution, climate change, and ecological degradation.
Based on the alarming statement above, there are solutions to overcome these problems. Growing concerns about environmental pollution and climate change have led several countries to implement stricter emission reduction targets, which has accelerated the use of electric vehicles or EVs in the road freight distribution sector. The logistic and distribution industry has adopted EV due to their environmental benefits, which aim to reduce carbon emissions and lower fuel costs. EV delivery vehicles are important in facilitating fast and sustainable delivery in urban environment. The full electrification of motorcycles has a significant impact on reducing air pollution in urban areas, contributing to environmental sustainability. By spreading zero-emission vehicles, it aligns the mission of a health-focused system with environmental responsibility. Replacing all gasoline-powered motorcycles with electric motorcycles can reduce fine particle emissions by 48%, CO2 by 23%, and CO by 13%. The electrification of public transportation has become a global priority in response to concerns about climate change, urban air pollution, and the increasing demand for sustainable transportation solutions. Therefore, governments and organizations around the world are accelerating the transition from internal combustion engine buses to electric buses. Through ambitious decarbonization policies. In improving the sustainability of transportation systems, which has attracted academic attention, electric vehicles have emerged as an urgent solution due to their environmentally friendly characterization. Electric vehicles are increasingly being promoted as a clean alternative in the national carbon neutrality target. EVs can eliminate exhaust emissions, improve urban air quality, and reduce greenhouse gas emissions. Therefore, electric vehicles such as motorcycles and cars are used an appropriate alternative to reduce dependence on fossil fuels, which cause significant greenhouse gas emissions.
The International Energy Agency, or IEA, published the Global EV Outlook of 2024, which projects global EV sales to reach 17 million units in 2024, representing more than 20% of total automotive sales. The development of electric micromobility vehicles, or EMVs, including electric bicycles, scooters, and mopeds, has significantly changed urban transportation patterns, especially in meeting the needs of short-distance travel and the food delivery service industry. Based on market research, the global EMV market in 2022 is projected to reach $33 billion with an anticipated compound annual growth rate of 9% from 2023 to 2030. In China, more than 7 million drivers rely on the EMV vehicles every day and often travel more than 1,000 kilometers per day.
However, several challenges have arisen relating to limitation of these electric vehicles due to the increasing adoption of electric vehicles in the logistics and transportation sectors. Researchers have been encouraged to explore various methods to overcome challenges related to limits battery capacity and long recharge time. The rapid adoption of electric vehicle is hampered by limited range, inadequate charging infrastructure, and unpredictable access to charging facilities. The implementation of electric vehicles in long-distance transportation and time-sensitive distribution remains challenging due to limited battery capacity and long charging times. Traditional electric vehicle charging methods have issues such as increased fire hazards, vulnerability to battery theft, and constant range anxiety. Limitations such as lower travel range, long charging time, and charging safety issues are hindering further electric vehicles development.
Further limitations to the adoption of electric vehicles, or EVs, are due to limited range, typically less than 100 km, long charging times, and EV charging safety issues. The most prominent challenge is also experienced by electric buses, namely limited driving range, which requires periodic recharging and risks disrupting service schedules. EVs can easily access charging stations to recharge their batteries, but they need to wait in line if all charges are occupied. Furthermore, the charging time for electric vehicles also varies depending on the power capacity of the charging point and the size of the battery.
Based on the above statement, some of the problems and challenges experienced by electric vehicles are related to long battery charging times, limited range requiring careful route planning, and limited battery capacity. Therefore, a proposed technology in the form of a battery swap station or BSS has emerged. With this technology, chargers do not need to spend a long time charging the battery, but only need to swap the battery. This is certainly an effective solution to overcome these problems. However, there are still considerations to be made to improve the efficiency of using this BSS. Problem statement. First, the distribution and logistic transportation system is still dominated by fossil fuel vehicles that produce high carbon emission and contribute to air pollution. Second, the transition to electric vehicles is still limited due to uneven charging station network, long battery charging times, and the need for efficient route planning for maintained battery life.
Third is this infrastructure limitation cause operational inefficient for electric vehicles in distribution and transportation. Fourth, innovation in battery swap station system is needed to enable quick battery exchange to improve efficiency, reduce waiting times, and support the sustainability of electric transportation. Fifth, the development of these systems must also consider aspects of professional ethics, technological safety, and intellectual property rights or IPR awareness in transportation innovation.
Objectives. First, analyzing the potential application of battery swap station as a fast charging solution for electric vehicles. Second, reviewing literature related to technological developments and implementation challenges. Third, building route and waiting time optimization models for swap station system. Fourth, reviewing aspects of professional ethics and intellectual property rights or IPR awareness in sustainable transportation innovation.
Development of electric vehicles and battery infrastructure in engines. First, electric vehicles. Air pollution from fossil fuel emissions has become uncontrollable, with the transportation sector contributing about 15% or 8.9 gigaton of global greenhouse gas emission. Fossil fuel vehicles consume vast amount of oil and release large quantities of carbon dioxide, making a global transition in the transportation sector essential to reduce pollution and dependence on fossil fuels. Many countries are now supporting the development of electric vehicles or EVs over sustainable transportation by significantly reducing carbon dioxide emissions through the use of cleaner energy sources. Their environmental and economic advantages, such as lower emission and reduced fuel cost, have increased interest from both government and the public.
As a result, government efforts around the world to promote electric vehicles have become a surefire pain to reduce emissions from the transportation sectors, address public health issues, tackle the broader risk of climate change, and accelerate the adoption of renewable energy sources. The development of promotion of electric vehicles can bring about tremendous progress and improvement. We estimate that electric vehicles will account for around 30% of total vehicle sales by 2030. Although the electric vehicles market is still relatively small in some areas, positive signs of growth are evident. The Indonesian government itself is determined to take concrete steps to reduce carbon dioxide emission and address global climate change through the promotion and use of electric vehicles among the public.
To improve efficiency in electric vehicle operation, an adaptive coordination system has been designed that uses fuzzy logic control, which integrates energy storage with superconductors. The energy management system also efficiently reduces power waste. The use of a hybrid energy storage system in a frequency regulation process links charge level management with droop control integrated with feedback from the charge level. By utilizing fuzzy logic control, the energy flow between the wheel system is regulated to be more effective in meeting performance requirements. Previous research emphasizes the importance of innovative approaches to optimize energy management system control in energy storage for electric vehicle technology.
2. Energy and thermal management in HESS system. In EVTs, regenerative braking converts kinetic energy into electrical energy, which is then stored in batteries or supercapacitor. Efficient energy distributor between the two is essential for improving overall power efficiency and extending battery lifespan. HESS combines high-energy batteries with high-power supercapacitors, while supercapacitors handle rapid power demands such as acceleration and braking, reducing stress on the battery. Temperature strongly affects their performance. High temperatures increase internal resistance and side reactions, while low temperatures reduce ion mobility and slow charge transfer. Such thermal stress can cause lithium plating and capacity degradation. Therefore, effective temperature management is crucial to maintain performance and prolong the lifespan of HESS.
Advantage and understanding the ethics of electric vehicles is essential for supporting their adoption, including environmental benefits, improved vehicle functionality, positive perceptions of green technology, and enhanced driving experience. With global warming and climate issues becoming increasingly urgent, reducing greenhouse gas emissions and developing clean energy have become global. Traditional combustion engines vehicles are major contributors to emission and urban air pollution. In response, automotive manufacturers are intensifying efforts to develop electric vehicles as a cleaner and more sustainable alternative to fossil fuel vehicles.
Disadvantage. The main barrier to electric vehicle adoption is the high upfront purchase cost. Although subsidies exist, they vary across countries and are often insufficient to offset the initial expense. As seen in Sweden, EV ownership is more common among higher income, well-educated individuals living in suburban single-family homes. The high purchase price also poses challenges for people with disabilities who require customized vehicles, making EV adoption less accessible for certain groups.
Definition of battery swap station technology. A battery swap station is a battery exchange facility that offers a permitting process for recharging empty EVs, where empty batteries can be exchanged for a fully charged batteries in just a few minutes. To meet the increasing demand for electric vehicles, one approach is to exchange empty EV batteries for charged batteries at battery swap stations. The main task of BSS is to replace the batteries of incoming electric vehicles, but it also acts as a backup storage in response to demand, working with renewable resources to achieve a dynamic supply-demand balance, lower cost, and optimal use of renewable generation. One of the technological aspects of BSS is optimal battery management within the station, which ensures service quality and maintains long-term health. Thus, BSS is used as an alternative solution to conventional charging, which has various negative impacts.
Transition from conventional charging system to substation, there are two main techniques for recharging electric vehicles. Conductive recharging and battery exchange mechanism. Conductive charging is quite slow and inefficient because it takes about an hour to recharge the power source. While battery swapping only takes a few seconds to replace the battery, there is also a serious rise when a large number of electric vehicles are charging at the same time, which can cause a severe new peak load and the local distribution network, putting additional pressure on transformers and cables and increasing network loss.
In 2021 in China, there were approximately 18,000 AMD-related fire incidents, some of which were related to charging accidents. EVs can easily access charging stations or CS to recharge their batteries, but require premium time if all chargers arrive at the same time. Charging times vary significantly depending on the power capacity of the charging point and the size of the battery. For example, a level 1 charge typically takes about 4 until 11 hours to charge battery from 5 until 15 kilowatt hours. A level 2 charge 19 kilowatt takes 2 until 3 hours to charge a battery up to 50 kilowatt hours. A level 3 easy fast charger 50 kilowatt can charge a 50 kilowatt hours battery in a half until 1 hour, and even a supercharger can recharge a Tesla vehicle to about 80% of its battery capacity under optimal condition in about 20 minutes. Super fast chargers can negatively impact battery efficiency and accelerate battery degradation, thereby shortening battery life, even though charging times are faster.
To overcome the obstacles of range and long battery recharge times, which are weaknesses, it is now very important to make a successful transition to sustainable transportation. The emergence of battery swapping as a promising alternative can significantly shorten energy recharge times and provide higher levels of service. The emergence of battery swap stations, or BSS, as a technological solution to accelerate the deployment of electric vehicles by simply replacing depleted vehicle batteries with fully charged units in minutes, and eliminating the delays typically associated with conventional recharging, thereby reducing downtime and range anxiety, and enhancing user experience and operational viability. However, BSS also faces significant challenges such as power coordination and efficient battery availability, and the high operational costs required to coordinate energy efficiency. In addition, energy storage also triggers battery degradation issues, namely the gradual loss of the battery's ability to store and discharge electrical charges over time due to repeated charging and discharging cycles.
Technical aspect of battery swap station operation. The battery exchange mode is analyzed as follows. When an electric bus is running, the power is detected to be insufficient for the next route. The system automatically sends a notification to the driver to replace the battery. On confirm, the system will send a reservation to the relevant BSS, and the empty battery enters to queue the way to be recharged for recycling. There are 4 battery classifications during exchange modes: full charged batteries, batteries waiting to charge, batteries being charged, and batteries being discharged. After receiving the empty battery, the battery swap station automatically adds the vehicle to the queue to wait for charging, at which point the charger or discharger connect the network and distribute PV and two direction to charge and discharge the battery. The battery is transferred to a full charge battery pack after being full charger to meet the electric bus exchange demand. If the battery still has power and exchanging, the system automatically discharges the battery, and the empty battery enters to pool to wait to be reached for recycling.
There are three types of battery at BSS. Depleted battery disconnected from EVS, fully charged battery ready for consecutive use, and battery with some energy remaining from the previous hours. According to Europe et al. In 2025, the station manages users based on the number of available slots and the length of the queue following the first in, first out or FIBO logic. After that, users exchange their depleted batteries for fully charged battery by waiting a maximum of 5 minutes for the batteries to charge, which can be their own or another slot depending on which one is charged first.
Next is economic aspects of BSS technology. The financial sustainability of BSS is highly dependent on hardware architecture and operational performance. The high initial cost of battery exchange station is due to spare batteries and robotic machines for heavy battery exchange operation. The details of this cost are capital costs, including the cost of replacing cabinets, battery packs, passenger cars of two-wheeled vehicles, and charging infrastructure. Software costs, including battery status management, charging, health, degradation, and finance. Land cost, including battery swap station locations, and operational cost, depending on personnel, office, maintenance, after sales, and utility costs. Adding BSS to smart microgrids that integrate with renewable energy sources and utilities and make the best use of used batteries can improve economic efficiency and support the circular economy. In microgrid development, this system optimizes hybrid energy systems consisting of diesel generators, solar, photovoltaic modules, and batteries, which can save up to 43% in energy compared to diesel systems and cut annual costs by up to 38%, thereby improving both economic and environmental sustainability.
Next is advantage of BSS technology. Some of the benefits of BSS include a more environmentally friendly from the energy, centralized battery management for longer battery life, and lower charging costs with a time of use systems. BSS enables rapid battery replacement within minutes and facilitates controlled charging outside the grids, thereby extending battery lifespan and reducing peak electricity demand. Several advantages of BSS can be a viable solution for the network support asset mobility in the future, such as enabling to mitigate network pressure while maintaining user autonomy, managing battery asset more efficiently, and reducing initial costs for users. While the weakness and potential negative impact of BSS is the establishment and operation of BSS or battery exchange station incur significant costs. The post-major obstacles, such as inadequate battery standards, inadequate facility costs, and operational challenge in monitoring battery accessibility.
Once at the charging unit, the battery swapping process is extremely easy and takes less than a couple of minutes, saving users on cost as well as long hours of recharging a conventional fixed battery-powered e-vehicle.
System optimization. First, optimization of station location and number or location optimization. The placement of charging and exchange station is very important in the advancement of EV infrastructure, which can be influenced by various factors such as economic, social, environmental, and technology. With the rapid growth of the EV market, the integration of charging and exchange station has emerged as an important tactic to improve infrastructure. A multi-stage location selection method based on multi-attribute decision-making or MADM technology and geographic information system or GIS, which is also integrated with multi-criteria decision analysis or MCDM. The optimization process can be carried out through a six-stage approach from initial screening to final validation with the aim of developing scientific accuracy and, of course, decision adaptability in BSS location selection.
Q optimization. Monte Carlo simulation is used to account for the uncertainty of EV arrivals in order to determine the ideal battery of range required in BSS. That utilize theory models to assess the efficiency of electric vehicles queuing for battery replacement services. Using the following data features. 1. Using empirical data to determine the average EV arrival rate. 2. Determining the load on the BSS and the average service duration of EVs. 3. Determining the SOC or state of charge of empty and recharged batteries. 4. Determining energy price to interval according to TOU. And 5. Analyzing data with hourly precision as feedback for the recommended model. There are several ways to optimize the design and scheduling of BSS for EV, where BSS has dual role, namely functioning as an efficient infrastructure for fast charging and source of dynamic energy storage. Several approaches that can be taken care.
Indonesia has committed to cutting GHG emission by 31% on its auto up to 43% with international assistance. Although electric vehicles are seen as important strategy for reducing emission, they are not yet formally included in Indonesia. Even so, the government has intensified efforts to promote the domestic electric vehicle sector through various policies, most notably President Resolution in number 55 in 2019, which support the production and use of battery electric vehicles. Additional regulation from multiple institutions further reinforce this direction, but more research is needed to evaluate how effective these measures are in enabling sustainable electric vehicles adoption from both government and public perspective. The encourage electric vehicles uptake, many countries combine financial incentives with non-financial benefits as road priority or traffic access. However, not every nation offers both types of support. Studying Southeast Asia, especially Indonesia, provides valuable insight due to its large market and strong evidence link consumer behavior with electric adoption.
Next is technological development. Modern civilization has long relied on fossil fuels in the transportation sector, causing carbon and greenhouse gas emission, thereby accelerating global warming and some climate change. Pressure from various parties has prompted the search for sustainable solutions, answered by the advent of electric vehicles or EV. Electric vehicles eliminate tailpipe emission and reduce carbon footprints, especially when using renewable energy. Their adoption is supported by the government incentive and advances in battery technology, marking a major shift toward cleaner mobility. However, the mass adoption of EVs is hampered by the challenge of charging infrastructure. Conventional charging systems result in long waiting times and range anxiety, which hinders long-distance mobility. To overcome this, innovations such as a battery swap station have emerged. This technology allows batteries that are almost depleted to be exchanged for fully charged ones in a matter of minutes, equivalent to refueling. Swap stations complement the existing charging ecosystem rather than replacing it. The future of electric transportation will be marked by the harmonious integration of residential and public charging networks for routine, fast charging on main routes and for commercial vehicles. This development represents a dynamic technological adaptation for process from problem identification, solution, challenges to innovation that collectively drive the realization of practical, efficient, and inclusive zero-emission mobility.
Policy on BSS development regarding the development of electric vehicle charging station, namely BSS, especially those that provide fast charging. It is crucial to encourage the acceptance of electric vehicles. Find the most effective locations for fast charging station using a multi-stage stochastic integer programming method. The goal is to meet unexpected charging needs while remaining within the exciting investment budget. Furthermore, developing this model also optimizes the location of public fast charging stations and shows that although most BSS are located in city centers, expanding by network by establishing BSS in suburban areas can be the best option and at a lower cost. Battery swapping is also considered an attractive solution to reduce the possibility of battery damage. In the concept of consumer concerns regarding fast charging services, the acceptance of electric vehicles in the market will be the best solution if charging speeds, mileage, and the number of charging stations reach a sufficiently high level. As for the interaction between the government and charging service providers, combining consumers' concerns about inconvenience and showing that the government can subsidize consumers or combine it with subsidies for providers. The government needs to provide subsidies for stations to address consumers' concerns about station availability only if the adoption target and the construction costs are both significant.
In addition, the government provides financial assistance for purchases as the main way to promote the use of electric vehicles. In the context of the proposed BSS-based electric vehicles, there are three tax incentives proposed by the government, namely tax exemption for BSS businesses, tax exemption for vehicles owners, and subsidies. The various policies have an impact on reducing operational costs, as this is a major barrier to the affordability of BSS-based electric vehicles. The elimination of taxes for BSS businesses could reduce operating costs by up to $35 and $28 per month in 2030. This reduction occurs because lower BSS operating costs lead to savings in subscription costs without changing the fixed IPR. In addition, the elimination of vehicle taxes is implemented to reduce operating costs, although it only slightly reduces operating costs. When combined with the elimination of BSS taxes, BSS-based electric vehicles become more affordable and accessible to many people. Finally, subsidies are estimated to be charged on operating costs to match the affordability of the second quintile. These subsidies are hypothetical and are used to estimate the amount of government funding needed to make electric vehicles affordable for the second quintile. Thus, a substantial subsidy is needed to cover operating costs so that a broader income group can own electric vehicles. Is the lifelong learning. Technological developments, from pollution issues to the emergence of battery exchange stations, are progressing rapidly and dynamically. In this environment, the sustainability of the career of an engineer, logistic manager, or a system designer no longer depends solely on the knowledge they have acquired. The ability to continue learning throughout one's career is key. Every time there is a new breakthrough, an up-to-date understanding of materials, working methods, and evolving business models is required. Without a commitment to continuously updating one's knowledge, a professional risks falling behind and being unable to contribute to finding solutions for the future. This lifelong learning is not only covered technical example or aspect, but also other supporting matters. For example, an engineer who designs a battery exchange station also needs to understand how to determine the right location and estimate user needs. A logistic manager must learn how to manage a sustainable battery supply chains and the battery rental business's model. On the other hand, system designers need to understand the ethics of technology application and legal aspects such as intellectual property rights. Thus, this learning combines technical, managerial, ethical, and legal aspects so that an innovation is not only technological advanced but also commercially viable, fair, and legally protected. The relationship between continuous learning and innovation, such as battery exchange station, is mutually supportive. Battery exchange technology itself was created thanks to the ability expert to learn from the shortcomings of conventional charging system and adapt knowledge from other fields. This learning process is ongoing. The next generation of battery exchange station will require an understanding of integration with smart grids, the use of artificial intelligence for maintenance, and new standards to ensure all systems can work together. Therefore, the spirit of continuous learning is not only an individual responsibility but a principle that enables the entire industry to adapt and innovate. In addressing major challenges like climate change, the commitment to continuous learning is the primary driver, ensuring the creation of that one breakthrough after another.
Thank you for listening to our presentation
And goodbye!